Yesterday, we did a little bit of an analysis on two-dimensional conservation of momentum. We didn't crunch any numbers, we didn't do any calculations, but we established that a two-dimensional collision, a T-bone collision, as we looked at yesterday, was exactly the same as all of the problems that we've done until this point, except more work. Okay, we looked at a problem where object number one was moving towards a stationary object number two, and then we did a problem where we had a stationary object number one where object number two was moving towards it. We know that when we have this first problem, we say Pi is equal to Pf, or M1 V1I plus 0 equals M, assuming they stick together, equals total mass times the final velocity. We know in this problem that 0 plus M2 V2I equals the total mass times Vf. That is, again, if they stick together, only one object after the collision. But we also know that if we combine these two problems, object number one is moving to the right, object number two is moving downwards, as it is in the second problem there. They stick together after the collision and go off somewhere down here. We know that we can analyze this problem in exactly the same way as we analyzed the first problem and the second problem. We just have to do both of them, that's all. When we're analyzing the x component, which is what we got to do, separate it into x and y components. We're going to analyze it by taking what we did over here and just moving it over here. Okay, there's my x component. When I go to analyze my y component, I'm going to do the same thing except take this analysis and move it over here. You see how this problem, this two-dimensional problem, is exactly the same as the first two problems that we put up on the board there. The x component has zero momentum for the second object. Hey, can you explain to me why I can do that? In the first problem, it's easy to say why the second object has no momentum. It's not moving. But in the third problem here, the second object is moving. How can I say that the momentum of the second object is zero there? Good, it's only moving downwards. Okay, while we're looking at the x component, we're pretending the y component doesn't even exist. Okay, there's nothing there for the y component. Now, similarly, when we're looking at the y component, we're pretending the x component doesn't exist. So if we're pretending the x component doesn't exist here, then the initial momentum of object number one will be zero. Does that make sense? All right, so what do we do with this once we've analyzed the x and the y component there? Once we've got a final velocity for the x component, once we've got a final velocity for the y component, what do we do with those? Yep. Good. We'll recombine them. We're going to go back to physics 20 now, right? This is the easy stuff. Let's just do a little bit of a vector analysis that we did back in physics 20. We take our VF x, we take our VF y, we combine them by doing the Pythagorean theorem to get VF and using the inverse tan function to get theta. Does that make sense? You got to understand here, first of all, understand this problem mathematically. Okay, we can do this problem mathematically. But bigger picture here, okay, we've got to understand, just like we saw in that movie, Django Unchained there, the little scene from it, where the gunshot was fired this way, the person flew off, the person that was hit by the bullet flew off this way. We've got to understand, okay, at a deeper level than just the mathematics of it, that if you have something going to the right, x momentum, and you have y momentum, here's the x momentum, here's the y momentum, then you've got to have the same x momentum after the collision and the same y momentum after the collision. In other words, you've got to have an object after the collision with a momentum that has both x and y momentum in it, giving us roughly this direction. All right, let's take a look at a problem here. There's a couple angles here that aren't going to make a lot of sense to you right now. That's okay. We're not going to lose any sleep over the notation that they use for the angles. I'll explain it to you. You don't need to worry about memorizing the way that works. Although, to be honest, it's not that hard. It's just that we won't see it on our diploma exam. So or on our unit test, so we won't worry about the notation. Okay, we're more worried about the diagram and the bigger picture here. And they give two angles here, 0 degrees and 270 degrees here. If I draw an XY coordinate system here, then we would label this as 0 degrees. Going around counterclockwise, this would be 90 degrees, this would be 180 degrees, and this would be 270 degrees. And if we keep going on, then this would be either 0 degrees, or we could call it 360 degrees as well. Again, don't lose any sleep over that. Okay. Let's draw the diagram here now. We got a 90 kilogram quarterback. We're going to call him object number 1. "90 kilograms. He's going at 270 degrees, which would be downwards on the page, at 8 meters per second. No, he's not. 7 meters per second. 7 meters per second. We've got another football player, 110 kilogram linebacker, running at 8 meters per second at 0 degrees. So object number 2, the guy who's 110 kilograms and moving at 8 meters per second, going at 0 degrees, as we have it labeled in the diagram there. Now, if these two guys stick together, they embrace each other. Two football players, they're embracing each other after the collision. They're not really, actually. Okay, they're not telling us that they're going off as one object here, but they are telling us that we want to find the velocity of the center of mass of both of those football players. If we want to find the velocity of the center of mass, we're pretending, in a way, that it's going off as one object. The center of mass is where the mass can be considered to be concentrated. So if you're going off as separate objects, since you consider the mass to be concentrated here, that's where the mass would be if you went off as one object. Okay? So if you ever see that whole center of mass thing, just pretend it's one object, even though it's not really. Where do you think they're going to go? Where do you think these two big football players embracing each other after a collision are going to go? Tucker? We don't need an exact angle. I don't want an exact angle. I just want the rough. Okay, down and to the right. So we're going to predict it's going to be down and to the right. You know what? That's a prediction, but it's not a guess. We know for sure they're going to go down and to the right. If we had X momentum before, and we do, and we had downward Y momentum before, and we do, then we have to have X momentum and downward Y momentum after the collision. We have to. At exactly what angle? We're not sure yet. We got to do the calculation to figure that out, but we know roughly where they're going to go. All right, so let's do this now. Let's break it up into our X and Y components. Remember, as we're doing X, we're pretending that Y doesn't even exist. You can scratch it out if you want. Cover it up with your hand. Cover it up with another piece of paper. Okay, cover it up with a calculator, whatever. There are two objects, but the first object has, what's the mass of the first object? 90 kilograms. What's the velocity of the first object? 0, right? Because it's on the y-axis, and we're only looking for the x-axis here. So we're going to say the first object has 0 momentum. The second object has m2 v2I worth of momentum. Now, we're pretending they stick together because we're looking for the velocity of the center of mass. So we're going to combine them into one object, mvf. 110 times v2I is 8, equals, the combined mass is 200, times vf. Vf is going to be equal to 110 times 8 is 880. 880 divided by 200, I think, is 4.4. Is that right? 4.4 meters per second. Is that a final answer? No, it isn't. But you know what? If this is a multiple choice question on a test, there's a pretty good chance that that's going to be one of your options. Right? You get that far, you say, oh, 4.4. Hey, that's one of my options. It must be right. I better pencil that one in. You finish the question. Okay, don't get thrown off by that. They do that to us lots, right? We see an option. Okay, we saw that number somewhere as we were working on the question. It must be the answer. But it's not. Let's do the y component now. Pi equals Pf again. Object number 1, what's its mass? 90 kilograms, right? What's its velocity? What is it? Cool. 7? Almost. Almost. We're not going to make it 7. We're going to make it, no, I'm positive you know this. -7. We're going to make it -7 meters per second because it's going downwards, right? The mass of the second one is 110 kilograms. What's the velocity of the second one here? Bailey, what's the velocity of the second one for the y component? Kelsey? I'm sorry? 3.15? What's the velocity initial for object number 2? No. You think you found the final? 8? No. Janessa? 0. 0, right? How much of that 8 meters per second is on the y-axis? Remember, guys, when we're looking at the y-axis, we're pretending the x-axis doesn't even exist. Erase it. It's gone. Okay, there is no momentum of object number 2 before the collision on the y-axis, just on the x-axis. Okay, well, they do combine, and afterwards we do have 2 objects, not entirely on the y-axis, but at least partially on the y-axis. Okay, we got 90. We established that was -7. The combined mass here is 200 kilograms again, times VF. 90 times -7 is -630 divided by 200 is 3.15, -3.15. Now comes the physics 20 work, right? We got 4.4 meters per second. How did I know to draw that 4.4 to the right? How did I know to draw that 4.4 to the right, Janessa? Because it's positive, right? 3.15 goes downward. How did I know to draw that 3.15 downwards? Lewis? Because it's negative, right? Now, I don't need to label it as negative here. The arrow tells me it's negative. The arrow tells me it's down. Okay, on my diagram, I could just make it a positive. Let's find the value of V by doing the Pythagorean theorem. And let's find the value of theta by using the inverse tan function. We have the opposite, and we have the adjacent. Let's say this half of the room right here, you guys get V, okay, using the Pythagorean theorem. This side of the room right here, you guys are going to get theta using the inverse tan function. Make sure you're in degree mode in your calculators, not in radian mode. Somebody have an answer for V on this side of the room? Yep. Okay, 5.4 meters per second. Anybody agree with that? It looks reasonable given the 2 numbers that we have there. Yes? Okay, what about theta on this side of the room? Okay, so what do we get for theta there in the calculation? Let's not worry about the 324 yet, but 35.599. Okay, 36 degrees. 2 digits, 36 degrees. Now, John said what? 324? Okay, now, John's expressed that in the notation that they used in the question, right? So basically, if this is 0, this is 0 or 360, this is 90, this is 180, this is 270, then this angle right here is going to be 360 degrees minus 36, which would be 324. So to express it in the notation that they used, John, you're right, 324 is correct. Again, I don't really care about that. If you can calculate that angle 36 degrees there, that's fine. You're good there. Now, somebody else say they got 64 degrees? Or no, 54 degrees? Did I hear somebody say that? 54 degrees be a correct answer. Could it be? How? Yeah? Yeah, so basically what we're saying is, well, if you do your diagram like this, which is correct, doesn't matter whether you draw x-axis first or y-axis first. If you draw it like this, You're going to calculate that angle and you're going to get 54 degrees. Okay? And that's correct, right? According to your diagram, that's correct. Yep. No, that's a good question. Let's not say south of east here, okay? Let's not say 36 degrees south of east. The reason is because the frame of reference in the question is not a north, south, east, west frame of reference. Okay, we only want to use south and east, south of east or east of south, if it's a north, south, east, west frame of reference to the question. The good news is, if this is a question on an exam, they're not going to give you an option 36 degrees and then another option 36 degrees south of east. Okay, they're not going to try to do that. So you'll, on an exam, you'll get 36 degrees and you'll look at your options, you'll say, oh yeah, that's it. Just be careful though, if you get to 54 degrees, right? Which one is it? Depends upon how the context of the question. Right? You'd have to look at the context of the question to know which one you wanted. 36 degrees. All right, you guys feel okay with that? You guys felt fine with this, right? The week before the break, as you were working on conservation momentum, you felt fine with this. You must have felt okay about this in Physics 20, otherwise you probably wouldn't be in Physics 30 right now. So if you're okay with this a week ago, and this a week ago, and this last year, then it's just a matter of doing three things at once here. Here's the good news. We only have 2 practice problems for you to do. Here's the bad news. Each practice problem is kind of like having 3 questions. So it's kind of like you got 6 practice problems here. Let's see what we can do with those over the next few minutes, okay? Just a quick little reminder, 180 degrees is which way? Position 1, 2, 3, or 4? Position 3, right? 180 degrees is position 3. 90 degrees is position 1, 2, 3, or 4. Position 2. And down here we've got just west and south. So, Lewis, you asked a question a few minutes ago, south of east, whatever. We wouldn't express it as south of east, south of west, whatever, in question number 1 here, because of the frame of reference they've used. But the question number 2, a frame of reference is a north, south, east, west frame of reference, so we would express it that way. Number 2. Does that make sense? All right, let's get at these questions, guys.